Alright, welcome back to another lesson. Physics, we are looking at module 8, inquiry question number 1. The document we're focusing on is to investigate the evidence that led to the discovery of the expansion of the universe by Hubble. Okay? So, let's just quickly have a look. The textbook reference we are dealing with is this one here. We're going to explore some of the evidence that led to Hubble's prediction that the universe was expanding, and we are going to actually try and describe and look at what each one kind of means. Now, to get ourselves started with this context, I want to firstly talk about what light year is. Okay, now light year is the distance between celestial bodies, so things in space. And to understand the distance, we know that the distance between planets is really big, but we also know for a fact that the distance between galaxies is way bigger, and you can't really predict that or explain that using just kilometers and meters. So we came up with a system called the light year, and that's basically how far light travels within one Earth year. So in about 365.25 days, how far does light travel? About 9.5 trillion kilometers. So that's a bit of context of when we talk about the distances. In terms of the predictions of the expanding universe, one of the greatest minds of all time, Albert Einstein, actually didn't believe the universe was moving at all. He actually believed the universe is static. Due to his work with general relativity. Now, there were a couple of scientists who worked on his equations of general relativity and believed, contrary, that the universe was expanding and that the general relativity formulas implied that there was an expansion. So that was that. But the main protagonist in this storyline that we're talking about today is Edwin Hubble. You might know him as the Hubble telescope. Well, not know him for, but the Hubble telescope is named after Edwin Hubble. Okay, and his ideas are quite revolutionary, or were quite important. We even represent that as the Hubbles Law, V over capital D or lowercase d, depending on where you read the textbook, and then H0. So he found that the speed in which the galaxies moved was directly dependent or directly proportional to the distance in which they were from the observer, and that would give us a nice little one. So what this formula is showing us here is the distance observed. So the observed distance that we see is directly proportional to what we call the recessional velocity. Basically, how fast is something moving away from us, from that particular spot that we see. That's what it's called. Okay? And the constant that we get here, so capital H, this is a constant. It's known as Hubbles constant. And looking at this, we can actually use this constant to help us predict how old is the actual universe. So we'll come to that in a second. Let's firstly look at some of the evidence he was working with. So the first part is investigate the evidence. Now you would have seen this in the previous lesson. So our little diagram over here with the cosmic background radiation. Okay. But there's some other things we can work with. Firstly, from back in year 11, when we first talked about the inverse square law and how brightness will change over time, it's a really interesting thing we can work with. So say if I know the brightness, so let's just change that color. Say if I know the brightness at this point here. So at R3, I know the brightness or intensity is 9. Okay? Okay. I also know what the overall brightness of the original star is, or 1/9, and then I'll say the overall original brightness is 1. Okay? Now, with specific uses of mathematical models, we can actually work out what the distance is between our star, or how far the star is away, by looking at its actual luminosity, so how bright it is, how much energy it gives off, and how bright it looks when we observe it from Earth. So we have this nice little formula here that shows us. We have M, which is the apparent brightness. Okay, we have capital L, the luminosity, so how much energy is being given off by the star, and then we have 4 pi r squared. Now that's obviously just the area of the sun, or any star that we see. So we're saying that the star, as it moves further and further away from the actual point source of giving off the brightness of light, light will just kind of expand in all directions. So expand in all directions like a circle migrating outwards. This direct relationship between our luminosity and apparent brightness can tell us this distance r here. Now r is actually the distance from the center of whatever star you're looking at to the center of whatever planet you're looking at it from. So in this case, it could be from Earth. So that's an interesting fact that we can use. So let's actually look at who used this idea. So we have a female scientist called Henrietta Lizard, and she looked at what we call variable stars. So as you can see from the animation here, variable stars are these stars in the universe that we observe that changes in terms of its brightness and dimness. So it could be brighter at a specific point in time, and then it could get dimmer. And you can see that certain stars that you study, you can see this effect quite promptly. So that's what we have here. Okay. Now, what we do know is these stars have a certain period in which it gets brighter, and then there's a bit where it gets dim, or at its dimmest point. So it will fluctuate. Okay. Knowing that fluctuation is quite important. Okay. So she studied what we call large and small magnetic clouds, what we know now as different types of galaxies, and all that. So just outside our own Milky Way, there happen to be these kind of cloud dusters that she was studying from. And what she found was the apparent brightness of stars, as you saw in the animation above or before. The brightness will fluctuate periodically. So there's a specific set time where it gets brighter and where it gets dimmer. Now, what she found is actually quite important. Okay, so what she actually found was similar bright stars. So stars with similar type of brightness had the same kind of fluctuating patterns. So the brighter the star, the longer the fluctuation in which the brightness of the star goes from bright to dim. But what she also found was the brightness of these variables increases as their period variation lengthens. Okay, you can also see that dimmer stars obviously a little lower fluctuations there in terms of days based on their brightness. Okay, so that's what she saw. You can actually show that in on a linear trend, how brightness of stars, logarithmically speaking, is directly proportional to the period in which the fluctuation occurs. Okay, so that's some of her findings. Now, why is this significant? Why is testing brightness? How often does this brightness fluctuate? Why is that important to the overall grand scheme of how the universe is expanding? Well, let's have a look. So stars of similar brightness, what she found, had the same period of time of fluctuation. Okay? What she actually found is not only that, but these fluctuations occurred from the same distance away from the Earth. So she found that if the star has the same brightness fluctuations, the overall distance would be the same. Okay, how do we know that? Because we, from the equation we talked about before, the apparent magnitude is proportional to 4 pi r squared. So if I know what this value is, our apparent brightness, and I know what they should usually be, the luminosity, then I can work out what the distance is. And we found that if it has the same brightness, it is equally far from the Earth. That's what we see. Okay? So the reason why it's so important is from now on, if I want to know how far away the star is, I can just look at how bright it is from my recordings from Earth. So that's a really important thing to have. Okay? So that's her contribution. And it's really important because a guy called Edwin Hubble used similar data, similar information that she used to look at a galaxy called the Andromeda. Now, Andromeda at the time, we didn't know it was a different galaxy. We didn't even think there was anything outside our Milky Way. Okay? We actually believed before this finding here that the universe was the Milky Way, our own galaxy here, but he found some very different things. Now, the important part of his investigation, not only he used Harriet's investigation of the time period and the distance of the stars, but he also used emission spectra, absorption spectra, and the Doppler effect. So let me give you sort of an idea of what he was doing here. So we have the spectral lines of the sun. You can see here. You can see with the spectral lines, some lines are, fatter and some lines are thinner. Okay, so that's what we see here. And we also see a different one for the similar type of sun, but for a galaxy that's much further away. Okay. So what we can see here is if we compare two suns, similar type of emission or absorption spectra, you can see that the sun or the star that's away from us or further away from us is more redshifted. So all of its absorption lines are further towards this right-hand side where the red light is. Okay? And that's a really important finding as well. So by comparing the wavelengths of the spectral lines of hydrogen, some from different galaxies, different nebula far away, and then comparing the exact same spectra of hydrogen in the lab, this is what Hubble was able to conclude using the Doppler effect. He could conclude that the relative speed of the galaxies was increasing as the stars were further and further away. Remember what Henrietta did. If you know the star is brighter, you know it's also further away from you, or you know exact distance of how far away it is from you. So if you know the brightness, you know how far away it is from you, and then you check out the emission or absorption spectra, and you see it's more redshifted, you'll see that the galaxies are indeed moving further away. So maybe I'll just write that down, just so everyone kind of sees what I'm talking about here. So we know that brightness tells distance when it comes to stars. Okay. We also know that with the distance, so stars with greater distance move away faster, And we know that because Doppler effect shows a bigger redshift. Not Doppler shift, a Doppler effect. So there's a greater Doppler shift, or Doppler redshift, sorry. So that's what we have there. Now, because he had a look at multiple different galaxies, he found that a lot of these galaxies were moving faster away from us, okay? Faster than anything that's inside our own galaxy. So if our galaxy holds all these different types of stars, and then we're measuring all these other types of stars that are moving a lot faster away from us, and it doesn't match any of the speeds in our own galaxy, that would imply that they are outside the galaxy we have. We actually have multiple galaxies. So the other thing you try to do, let's imagine that's a Milky Way, and you measured the overall velocities of the stars here, here, and here, and then he looked at other nebula outside of that, and he found that the velocity here was faster than the velocity we have over here. So the fact that the velocity was faster out here would imply that these fast moving objects must be outside the boundaries of our galaxy. Okay, so that broke down the idea that we only have one galaxy. There was actually multiple galaxies in the same universe. You can imagine it this way. You can imagine when the Big Bang first formed, you had little points, dot points in the galaxy. As the universe expanded, the galaxies holding up the same space, but they're moving further away from each other. And that's what we're seeing with the redshifts. So if they're already really far away to begin with, they're just going to be moving even further away from us at a much faster rate. This idea of it moving faster away from us, or this speed in which it's moving away, we call this the recessional loss. That's what we're looking at. Okay? So there's that. The actual formula to describe Hubble's law is this one here. So V equals H capital, which is Hubble's constant, times the distance between the Earth and the observed star. Okay, so this is what we have here. That's given by the following units. So pascals, or parts per seconds. If we actually have a look at the construction of the Hubble's constant, we can see that if we graph velocity over distance, velocity over distance, that is the Hubble constant. Okay? So what we're seeing is the Hubble constant here. Now, how do we actually predict? Well, we can see that the further away the galaxy is, okay, so the greater the distance out here, the greater the velocity. So let's imagine the Earth or the universe was moving at a very slow rate at some point in time. Let's bring it all back. If we kind of extrapolate back down, okay, we get to a point where the planet, or this point here, sorry, we get to a point where the space covered by the universe is very small. This point here is what we call the singularity point. You can also call this the Big Bang moment. So this is how we actually extrapolate backwards to work out that perhaps if the universe was expanding really, really big, there must have been a point where it was very, very small. Okay, so that's what we have here. If we inverse the gradient, so if we inverse this, this is the value we can use to find the estimated age of the universe, which we know is about 13 billion years old. So that's really significant finding. Okay, so he's using Henrietta's work, he's using redshift Doppler effect to work it out as well. All right, so we're looking at one of the past paper multiple choice questions. It says a typical galaxy has a diameter of 100,000 light years, 30,000 BC. Which graph is consistent with Hubble's measurement of recessional velocity of galaxies? Okay. The answer for this, and you can pause it if you would like, the answer is A. Okay. The reason why C and D cannot be correct is obviously the former itself, the Hubble's constant, represents a directly proportional relationship. So we said that the residual velocity or recessional velocity is Planck's constant over d, so they should be directly proportional to each other. So we should see a straight line. So C and D can't be correct. A is correct because in his actual measurements, he didn't use light years, he used PC, parseconds. Okay, so there's that. You can actually demonstrate the expanding universe. All you need is a couple of dotted stickers and a balloon, and then you can actually inflate the balloon and you can see the kind of distance changing between the positions of the stars. So that's something you could show. Okay, I'll let you work that one out. So now I'm just racing towards you. What do you hear? Why? And how is this effect applied in astronomy? So how do we use the Doppler effect? So just pause this video here, try and write something up, and then you can have a look at the response. All right, so there's that. So we know that as it approaches, this pitch of the sound will increase, so the frequency is going to go up. So we have an increase in frequency, and as it moves away, frequency decreases. The reason we use the Doppler effect is we can see where the colored lines are shifted, and that will give us an idea of the direction in which the star is moving and also how fast the star is moving to or away from us. Okay, next question we have is which star will show a normal spectrum of light? In this case, B, because it's stationary. Question B here, where will we see the redshift? So redshift is when the star is moving away from us, so star C. And which star will show a blue shift spectrum for light? That would be A, because it's moving towards us. Okay, so what are some other evidence that show the expanding universe? Mind you, this isn't explaining what Hubble did, because we already talked about what Hubble did. Hubble used the variable star magnitudes and also used redshifts, Doppler effect to work it out. These are other works that show the expanding universe, but not necessarily contribute to Hubble's work. So we have the cosmic background microwave radiation, and we have helium and hydrogen ratios. So why is that important? So the cosmic background radiation was emitted 13.7 billion years ago, and the reason why you see this kind of color contrast here, it's just scattered photons, so scattered radiation that we saw just before hydrogen was beginning to form. Okay, so the idea is obviously if you have this big radioactive event, radiation is electromagnetic waves. These are continuous throughout the universe, so at some point you should be able to observe them regardless of how long the event was, in this case 13.7 billion years. So that's very nice. Based on our deductions, the spectrum that we see, or the maximum emitted wavelength, matches the predicted temperature the radiation would be of today, which is 2.7 Kelvin. Okay, so if we take into considerations of the redshift, the average temperature is 2.725, so that matches what we see, and the black body spectrum matches the predictions of Big Bang theory, in which in that case you don't need to know the actual calculations, but the prediction of Big Bang theory was this expansion of radiation would eventually cool down and it will be microwaves. And if you use Wenz's law to put 2.725 into Wenz's law, you'll find that the wavelength you get is in the range of the microwaves. Okay, how does the abundance of light elements reflect the Big Bang theory? So if we model through early universe with the Big Bang, these are the following elements that you can form, okay? These are the four that you get. And following that, we actually can detect that a majority of these elements, light elements, were in existence when the Big Bang occurred. So again, our theory matched the scientific evidence that we found. So that's kind of how you explain through how light elements show for the Big Bang theory, matching predictions. And again, the cosmic background radiation again backs up our predictions. Again, this is also due to the Doppler effect. To show that photon scattering, should now be microwaves in that range. Okay, so there's that. You can go through these multiple choice questions at your own pace. So show the answer to B. I'll show the answer to C now, and the answer to D, and the answer to E there. Okay, so that concludes the lesson of showing what evidence did Edwin Hubble use to discover the universe was expanding. The main ones you really need to remember is obviously Henrietta's work with varying brightness of stars, and also Hubble's own work using the Doppler effect to work it out. Okay, there is a exam question I'd like you to try at the end of this lesson, so please have a go at that and see what you can muster out of it using the cube method. Until then, homework is there. Have a look. That concludes our Module 8 Inquiry 1 dot points. So use these videos, use the videos before in the same playlist to see what else needs to be filled out or if there's any gaps in between. Okay, until next time, practice hard and rewatch any videos if you are not sure.